você me pegar. Hello, welcome to our lab tour on the Advanced School in Quantum Fluids and Applications. You're going now to see a video that we have done to guarantee that at least you can see the highlights of one of the experiments in your lab, and then following the video, the ones that are presently here in São Carlos are going to come and enjoying the realization of a few BoseEinstein condensation experiments in real time, so they can see how everything is done. If they are not experimentalists, of course, they can have a very good idea how are the laboratories conducted to be able to produce all the results we have today in many laboratories around the world. So please enjoy the video. It takes about 30 minutes video where we give a few highlights of the laboratory in this experiment, and then later on those students or participants that are present can come to our lab and they're gonna see in real life everything that's going on. I hope you enjoy, and then we'll be here to answer any question you want. So let's go for the lab tour video and then the real lab tour. A BoseEinstein condensate is much more than just a phase transition, as we learn in courses of statistical mechanics, thermodynamics. Is much more than that. BoseEinstein condensation is today a whole field, is a workbench for basically investigation of many areas of physics. With BoseEinstein condensation, we can study statistical mechanics in the laboratory. We can actually see in action the so-called quantum statistics. With BoseEinstein condensation, we can test field theory, because that's a very nice example of symmetry breaking. With BoseEinstein condensation, we can study superfluidity in many, many aspects, from the formation until the development of the main macroscopic properties. With BoseEinstein condensation, we can study quantum phase transitions. We can create arrays of atoms that are originally condensate and manipulate the interaction in a way to produce transitions that before we could only do using theory. With BoseEinstein condensation, we can study thermodynamics, and thermodynamics of a very important regime, the regime of ultra-cold temperature. With BoseEinstein condensation, we can study even interaction in a regime where we cannot imagine atoms to be balls. We have to imagine large waves interacting each other. With BoseEinstein condensation, we can study sensors. We can develop ways of understanding gravity. With BoseEinstein condensation, we can study new fields of many-body theory, many-body quantum systems. With BoseEinstein condensation, we can study disorder and many other things we can study. So BoseEinstein condensation goes much beyond the phenomenon of BoseEinstein condensation. It's involved a large variety of areas in modern physics. And all around the world, people are studying BoseEinstein condensation, either on the theoretical aspect or in the laboratory. And today what we're going to do is a tour through an experiment of BoseEinstein condensation. What are the main concerns we need in order to produce a BoseEinstein condensate and in order to investigate some of these aspects? Here in our laboratory, we study a few of the many possibilities of studies with BoseEinstein condensation. We study thermodynamics, how this phase transition takes place, what are the macroscopic properties that we can actually measure, how is a non-homogeneous system behavior in that transition, because normally we put the atoms in a harmonic type trap. We study also the out of equilibrium. Normally Bose-Einstein condensation is a phenomenon in equilibrium. We put atoms and the equilibration, the presence of a distribution of possibilities in the occupation of the states, give it to the system special properties. And we study out of equilibrium, as I said, and turbulence, because Bose-Einstein condensation, as I said, is a very nice system to study superfluidity. And when we speak about superfluidity, there are intrinsic properties with superfluidity that are very important to understand a few things of the superfluid itself. But we go a little beyond. We produce disorder in the superfluid, going to the field of turbulence. But turbulence in superfluid, which is a quantum system, and therefore we call this quantum turbulence. And we investigate that. Normally, to start to plan a Bose-Einstein condensation experiment, we need, as you can see, a large variety of instruments that allow you to produce this very specific state of matter. So normally we need to reach very low temperatures. And to do that, the best way is using laser cooling. And let me start to say a few words about laser cooling, and then show to you what we needed to prepare, which means what is the main instrument we need for laser cooling, which are the lasers. Is any laser okay, or you needed to prepare the lasers in a special way? So we're going to start with the lasers and explain a little bit about laser cooling. But once you are able to produce a sample of atoms cold enough, which is the starting point, we needed to trap those atoms. And then there are many different ways of trapping. You can use magnetic fields, which is one of the ways we do, but you can use also light fields, which is the light traps. And that's the other way we do. And for that, you either need a special configuration of coils that produce a special magnet trap, or you need a special light field that produce the light trap. But that's just in the middle of the way through condensation. Once you put a sample of cold atoms inside those traps, you need to cool even further. And that cannot be done easily with the lasers. Even though nowadays you have a full optical cooling techniques for reaching Bose-Einstein condensation. We here do what we call evaporative cooling, which is one of the first propositions towards the way to obtain the Bose-Einstein condensation. And then you have the atoms trapped, you have to work out how to cool this down much further. And then there are, as I said, evaporation. And then we're going to show to you in details how the evaporation works. But once you evaporate, which means removing some atoms and hoping the rest of it cools down, you have to reach conditions where the Bose-Einstein condensation takes place. You have initially a gas that is distributed everywhere, more like the gas in the room, which is the Maxwell-Boltzmann distribution, classical gas. And then you start to cool down, and then the atoms with lower energy enough start to feel that they cannot have any possible energy. They need to start to accommodate in the quantum levels of the trap itself. And then they start to accommodate, and that's when the game starts. Because whatever the population of one of those states becoming macroscopic, the system will undergo a phase transition called Bose-Einstein condensation. And of course, the easiest way is put everybody in the lower possible energy state, which is the type of Bose condensate that we work. Now, you cool down, you may reach the Bose condensation, but that's not enough. You have to be able to observe that you have reached the BoseEinstein condensation. And there are many properties associated with a Bose condensate, which are like fingerprints for identification that you actually have there one of those Bose condensate samples. And once you detect that you have, you start your study with this sample. So you see, to really do some innovative study with a Bose condensate, you have to come all the way from preparing the lasers in an adequate way, producing the atoms in another adequate way, producing the trap, cool down, observe, and then you're ready to start studying the Bose-Einstein condensate. Many theoreticians start with the sample already done, but we experimentalists spend the most part of the time following all this way to be able to reach the sample and then start our study. Normally the laboratory can be divided in two parts. The lasers in one side and the machine itself in the other one, right? And the machine will have many parts as we're going one by one. But first, we're going to start with the lasers which are prepared in the other table, in the other room. Let's go see. Let's start showing to you the laser preparation that we need to go and obtain the Bose-Einstein condensation. If you look in this table, you're going to see a lot of yellow light, and that's the light for the element sodium, because sodium is the atom that we have been working with, is the one that we have chosen to do the condensation in this experiment that we are carrying on now, which is an experiment of quenching. Okay, so if you look on the table, there are many lasers that produce yellow light, many components that are essential to prepare the light in size or in frequency that are necessary to send by optical fibers to the other room where the condensation will take place. And it's mainly, you cannot even count very fast because there are hundreds of components that are necessary. But more important than the components, to do a Bose condensate, you need also many people working. So you have many people taking care of different things. In this experiment, we have 2 or 3 sources of yellow light. Those are 2 solid-state lasers and 1 dye laser. And normally now we are using only the solid-state laser, and they produce light around 590 nanometers. And, but the laser is very good, produce a decent amount of light, as you can see, but that's not enough. We produce the light, but that light needs to receive some preparation to be adequate to go and cool the atoms or trap the atoms or see the atoms in different stages of the Bose-Einstein condensate. So let's start to show to you, once the light is here, you're going to see that there are many elements, and part of those elements is to make sure that the wavelength of the light is fixed in one value. This is what we call stabilization of the laser light. And Kilvia, which is a laser specialist, will show to you how we make the laser to stay in a single wavelength, which is necessary to produce the Bose condensate, to produce the laser cooling and everything else.
Hi everybody, now we are in the BAC laboratory, and now here you have sodium and potassium. Today you are working sodium, and for that you need a special lasers, yellow light. So you need yellow light for cooling, and also imaging on other frequencies necessary for BoseEinstein condensation and detection. Okay, so we have here a laser that scanning frequency. So this is only for the power lock. So it's a special laser that you're gonna show afterwards. And as you have, I'll lock this cavity. So Edward, please. Edward, you will lock the cavity. So in this way, you have yellow light available for the experiment. Okay. So, but if you only have the light, okay, is enough power and so on. But also you need frequency stability, and you need a very precise stability on the frequency. Also a very precise value on these frequencies. For that, you use what that you call locking the frequency using PID system that is on this computer that I'm going to show afterwards. But for that, you need use spectroscopy of a sodium line that you obtain from a hot cell that we're going to show afterwards. Okay. So as you scan the frequency, okay, of the laser, so you have the absorption on sodium. That is the transition you need to lock the laser. So you choose this frequency and you lock on this peak. Okay, so you have all the absorption of the sodium line in D2 line, no, okay, but you lock in the first absorption. Okay, Edward, thank you. This red line now is the modulation that you put inside in the system, and you produce a dispersion signal that's necessary to lock the laser. So now, Edward, you're gonna lock the laser. So for this system, it's very simple, and now you are locked on this frequency, and we are able to make all things you need on the experiment. You can see on this oscilloscope, okay, a signal that's proportional to a magneto-optical trap, but is in this yellow signal is proportional to the intensity of even the number of atoms in the magneto-optical trap. That is our first step in the experiment. Okay, so this is very important. If Edwin turn off the locking, you're gonna see that the signal is not the same. You just lose atoms, so you lose the trap as you unlock this laser. If Edward lock again first, please. So you see the yellow signal, that is the magneto-optical trap being charged, no? Loading. Loading is the best word. Okay? So this is something that you do every day. It is the first time for the next steps of this experiment that we're gonna show further.
In order to know what is the right frequency that we need to put on the atoms, we need to test our laser beam with atoms. So to do that, we use here, for example, a vapor cell containing our atomic sample. This is a atomic sample of sodium atom in which we passing through the laser beam on the atoms, and when the right frequency is set on the laser, the atoms will start to fluoresce. So this is the point in which we know that our laser frequency is the right frequency interacting exactly with the frequency of the atoms. So here, for example, we prepare a setup of mirror and glasses in order to create a system of saturated absorption spectroscopy in which we observe that signal on our locking setup. So this is how we prepare our laser to put with the right frequency on the atoms.
Producing the laser in the right frequency, with the right level of fluctuations, everything, a very nice prepared laser light, then the light is sent through optical fibers to this place. Here, as you can see, we have a yellow light, which is the one that's going to interact with the sodium atoms. And you can see that the yellow light is divided in two parts. One part comes to the right part, the right side of the apparatus, which is the place where we prepare the atoms to be cold enough and to be in conditions to be trapped in the second part of the apparatus, which is this main chamber made of stainless steel, bigger than the first one. In the first stage, we produce vapor. This vapor is compressed in 2 dimensions and pushed towards a tiny little hole that passes through the other chamber. This is what we call a 2-dimensional magneto-optical trap. Using that type of technique, we are able to produce a continuous flux of slow atoms. Slow like 30 to 40 meters per second atom. Remember, at room temperature, they are at 400, 500 meters per second atoms. So this is a stage that's necessary because if they are not cool enough, we cannot continue the process. But once they are produced here, this continuous flux of cold atoms comes the second chamber. In the second chamber, besides the green light that you're going to learn what is for in a second, we have also the yellow light. And there we have lights coming from 6 independent axes in 3 different directions, counter-propagating, forming another magneto-optical trap. And this continuous flux of slow atoms are in condition to be captured by those 6 laser beams and produce a combination of trap and molasses that cools down and produce a kind of sample, a ball, containing many, many millions of atoms, sometimes even billions of atoms, in a temperature that now is much below what we start with. We are talking about atoms that are on the order of millikelvin. And at millikelvin, it's enough for keep the ball of atoms in one single place. And that, with that sample, we can now turn around this ball magnetic fields that are able to hold the atoms, producing what we call magneto-optical trap. That's the whole sequence of producing the laser, producing a continuous flux of slow atoms, and capture those atoms in condition to put in a magnetic trap. Once the atoms are in the magnetic trap, light can be turned off. But as you observe, we have here a green laser as well. Up to now, we only use the yellow light. And as you saw in the other table, it's not a single frequency yellow light. There are a few combinations because the atoms, they have different hyperfine structure. And if we pump the atoms to one of them, they stop interacting with the laser. So we have to repump to keep the atoms continuously interacting with the atoms to be able to act as a radiation force and cool them down and be able to capture. So, going from the preparation to the main chamber, as we call, the atoms are ready to be trapped. And we have a whole bunch of coils around that at the moment they are in low level to be able to produce this tiny ball of atoms at a little bit less than a millikelvin. And then they are cold enough that if we build up the barriers, magnetic barriers around, they will be magnetic trapped. But then I was telling you there is a green light. So that means that something else besides the yellow light is necessary for this technique to trap the atoms. And now I'm going to ask Dr. Patricia to explain to you why we needed this green light in this device to be able to trap the atoms.
So, as Vanderlei told you, the first stage on this experiment is to cool down the atoms from room temperature to something below a millikelvin. Once we reach these conditions, we are able to trap this with a magnetic field, which in our case is the simplest possible configuration we can perform experimentally. We have two coils positioned along the vertical direction, which are assembled in an anti-Helmholtz configuration, giving a linear gradient of magnetic field in which the atoms will then be trapped. Okay, so the atoms, we didn't tell you the full story, but the atoms, they have different internal states, which we can simply associate with a spin. These states, they have different properties, and some of them are magnetic trappable, some are not. So this is relevant for us when we reach regions of magnetic field in which the magnetic field is almost zero. Why? Because in that region, the spin of the atom is not anymore well defined. So usually it aligns with the magnetic field. So in the quadrupole trap we have here in the experiment that I'm schematizing the potential for you, the atoms oscillate in this potential and the spin of the atom is always aligned with the magnetic field. Once we reach in the bottom of this trap, the region where the magnetic field is equal to zero, this spin is no longer well defined and transition to other spin states can make the atoms leave the magnetic trap. And this will cause losses that increase when decreasing the temperature, making it impossible to reach the Bose-Einstein condensate that we want to produce here. So one solution that is well established in community is to use a laser beam with frequency far from the atomic resonance. That's why we use green light that is far from the atomic resonance of sodium atoms in order to create a repulsive potential, so a barrier that will repel the atoms from the center of this quadrupole trap. So we prepare this laser beam. You can see this on this side of the table, and we send it directly to the atoms crossing the main chamber in this direction. So this beam is perfectly aligned with the center of the quadrupole trap, as you could see on the image of the atoms with a small hole in the center that we will show to you later. And this will then create the conditions that will allow us to cool the temperature of this cloud by means of evaporative cooling and reach eventually the Bose-Einstein condensate in our system. So these are the sodium atoms trapped in our quadrupole trap. We are seeing them then in trap without any release time from the quadrupole trap. And here we have also the plug beam aligned at the very center of the trap. This plug beam is a repulsive optical dipole trap, so it's causing a repulsive potential to the atoms. That's why we see a hole here in blue in the middle of the atomic cloud that is displayed in red, representing that it's a very dense cloud of atoms trapped in the plug trap.
Once we have all the conditions and the atoms are trapped, as Patricia explained, using the plug to avoid losses on the zero field, we are ready to cool down even further using evaporative cooling. Evaporative cooling is a very interesting technique where lowering the potential or even introducing some radiation that are able to produce transition of the atoms from a trapped to an untrapped state. We can remove the ones that are able to reach high Hill parts of the magnetic field. Normally, by lowering a little bit the fields, we can also lower the potential and make sure fast atoms escape. And when fast atoms escape, they take away energy, and whatever is there cools down even further by rethermalizing. So once we have the sample in the trap, we start this process of evaporation. And normally when we do evaporation, we normally start with a cloud that is very big. And then as we losing the fast atoms, we get colder, but we are losing atoms. So this is shrinking more and more until we reach a condition that basically is so cold that something very nice starts to happen. Something very nice, a very dense center of the trap appears, and that is the condensation. Normally when we condensate, we don't put all the atoms in a single state. We can do very close to 100% atoms in a single quantum state, which is a pure condensate. But normally we have, as you can see here, in a yellow surrounding, and then a blue surrounding, which are atoms that are cold, but not in the condensate. This is what we call the thermal cloud. And if we go even further, we go down and down and down, and maybe we can reach a sample which has almost 100% of the atoms in the condensate. Well, once we condensate, we need now to see and make sure we have that. And one of the ways we do is by time of flight. Imagine that you have that dense sample that are in the condensate, or not. Let's find that out. What we normally do is now suddenly we destroy all the potential that are holding the atoms there. And then that cloud of atoms, cold cloud, is free to fly. And then we do what we call a time of flight measurement. By letting this cloud to expand for a finite time, for a finite extension of time, the ballistic motion of the atoms can reveal to us what actually was in there, in situ, that normally is very hard to see. And during the expansion, because you know our trap is not fully isotropic, it normally has a shape of a cigar. And when we start, we have a cigar type of shape. But now, the long axis of the cigar is on the vertical position. As the cloud expands, there is an inversion. Then the long axis is now on the horizontal. So there is an inversion of the shape of the condensate, or the shape of the cloud. And that inversion shows that actually this cloud is a quantum sample. When you have a quantum sample, we cannot think about only the ballistic motion of the atoms, but we have to think about waves propagating in space. And for waves, there is this very important phenomenon that whatever the waves is more squeezed, they diverge more, they diffract more. Therefore, in our condensate, because we compress more on the horizontal axis, it will expand faster in that axis, like diffracting more in that axis. And that's what causes the inversion ratio of the two aspects, the two dimensions of the cloud will invert. Whatever is short in the very beginning will be the longest after a time of flight. This is a very good indication that we have a condensate. And if we don't have a condensate, well, if you don't have a condensate, is the picture below. The cloud will expand, but always will expand in an isotropic way. Always keeping more or less, very soon after the beginning of the expansion, it reaches a condition where it expands isotropically, having the same dimension in both axes, no matter how it starts as a cigar shape. So this is a good indication of the condensate. And normally you cannot see here, but there is one part of the cloud that suffers this inversion of the aspect ratio. And there is another one which expands isotropically, which is the thermal cloud. And by looking to this, we can actually separate the fraction that is in the condensate, which means occupying a single quantum state, from the thermal component, from the thermal cloud, which are atoms occupying many of the quantum states of the potential. Well, so that's the whole tour of doing the condensation. One of the things we do immediately after getting a condensate is characterizing it. As I showed to you, you can extract from the image, and how we do this image is by absorption of a probe laser. We have a tiny laser that are resonant with the atoms, and we do absorption, and whatever it absorbs, we can identify the presence and the density of the atoms locally. But there is one thing we normally do is give a little kick on the condensate. And when you give a little kick on the condensate, it starts to oscillate because it is trapped in the potential. And by giving a little kick, it goes and comes back like in a pendulum or like in any particle trapped in a harmonic potential. And by looking to this, we can create a plot which will tell us with high precision what is the frequency of that potential. Because by looking at the oscillation, we are able to extract that. This mode of oscillation is called dipole mode. But it's not the only thing that happens to the condensate. As the condensate is oscillating, you can see that it gets smaller and bigger, smaller and bigger. And this is another important collective mode of oscillation of the density that's called breathing mode. So this breathing mode also can bring a lot of information to us. And but this is a simple condensate. Normally what we do in this stage is start to introduce more excitation. We go and put steering beams, we go and put shaking beams, and by introducing these disturbing fields on the condensate, we can produce vortices, we can produce many vortices, and we can even go to a turbulent regime in the condensate. Turbulent regime will affect many of those things, right? But looking to those oscillations, we already can get many information about the condensate itself. To excite the atoms in the condensate, we use many techniques. Shaking the potential is one of them, and that's the way we produce turbulence, in fact. But there is devices today that allow you to control the laser beam, and control the laser beam in a very precise way. One of those devices is called DMD, Digital Micromirror Device. This is the device. You have a collection of tiny little mirrors that the laser light passes through, and by controlling many lines of micromirror, you can make any shape on the laser beam you want. Those devices help us to introduce different types of potential on the condensate that can produce vortices, or can produce many vortices, or can even disturb the condensate in a way that we're going to observe the reconstruction of the condensate and so on. DMD devices is a very powerful device for introducing different potentials or different ways to excite BoseEinstein condensation. Just a demonstration, with devices like this, you can program the mirror to draw letters in the condensate and produce whatever you want. So this is what you see in dark is where the light is not there. Therefore, if I introduce this beam on the condensate, the atoms will try to be wherever is dark. And then I can write letters, I can do all kinds of construction using DMDs in the condensate. Hey, I hope you have enjoyed the video, the tour that we gave to you in one of the experiments here, the sodium experiment. And of course, before receiving the students or the participants that are here for a real-life tour, I have a few questions here. And one of the questions is from Dalila, and she asked me, I believe, she asked me, what is the belly on the absorption curve when you are getting the spectrum of the sodium to lock the laser, to make sure the frequency of the laser is in the right frequency. Okay, this is a traditional picture of this. And as you can see, we see many peaks. We have a cell, and the way to really get very good absorption peaks is doing what we call saturated absorption. And when we do the saturated absorption, we put the two counter-propagating laser beams in the cell in a way that when we're going to interact with the same atoms, and which are the atoms that are traveling perpendicular to the laser beams, one laser excites and the other laser then cannot be absorbed because the atoms that are at zero velocity with relative to the laser beam have already absorbed one of the beams, and then the other one, which we call the probe laser, pass through, and then you see the absorption decreases. Here, absorption, and when you stop absorption, it goes up. So we see a big absorption, which is a big profile, but then when we get in the specific transition here, we see the two lines, the two P lines absorption, right? And then, you know, you see the two dip on the absorption due to this saturated absorption effect. But when you get in between the lines, it turns out that the Doppler effect from atoms traveling towards the laser beam or going away from the laser beam, they have the same value. They have the same value, but with opposite sign. So atoms traveling this way or atoms traveling that way will feel the same Doppler effect with different sign. So when we get around the middle of the two lines, it turns out that the absorption increases because we are interacting with the atoms either going far away from one laser and or counter-propagating to the other. And then the absorption of the probe laser increases again, and you see now a peak going to the opposite direction of the saturated absorption. This is a well-known effect in the saturated absorption spectroscopy, and that's giving the reason for this peak in between. Now, this belly here that you see is part of the Doppler profile. As you scan the probe laser, you are passing through many velocities, and depending the class of velocity with more atoms or less atoms, you see more or less absorption. And when you reach precisely the zero velocity resonance, which is the resonance free of the Doppler, you get the dip on the absorption. And then we keep the, this is as narrow as we can get in a thermal cell, and then we come in here and we lock. If the peak here will be zero detuning. If we go a little further, we are blue. If we go a little before, we are ready. And then we can select more or less how to lock the laser in a precise slope of the saturated absorption curve. Okay, let me see some other questions. Okay, well, this is the future hologram laser. Well, I have to confess to you that I did not understand the question, but Of course, holograms are important, lasers are important, and everything we do, we learn more about lasers, and of course we produce better lasers, more stabilized lasers. Therefore, maybe we can produce even better holograms, that's for sure. And then there are some more questions. Oh, I have these two questions. And then I have one here from my student here. He told me how disturbing is the thermal cloud around the condensate. And well, the thermal cloud is part of the system. We cannot get rid of it, only if we go to zero temperature. And what is nice about condensation is a transition that happens in a final temperature. So you always have a portion of your system which has a thermal behavior. And then a macroscopic portion in the lowest possible energy is like, for that portion, is like being in the zero temperature. But because they are in thermal equilibrium, you have a portion in the ground state, which is the condensate, and another one surrounding, which is the thermal cloud. So the thermal cloud does not disturb. It is part of the thermal equilibrium in the system. And we focus in the condensate, of course, which is that core that you have seen, which has the Thomas Fermi profile and everything. But if we don't reach zero temperature, we cannot get rid of the thermal cloud. And we are interested in quantum mechanics at final temperature, so having the thermal cloud is a way to do many verifications. Like, normally it is a Gaussian type of distribution of energy. If that is disturbed, we know that the system is coming out of the thermal equilibrium that naturally is present in the condensate. So we're going to produce something funny with the condensate when it's depart from equilibrium and so on. Okay. Oh, is there any other question? Oh, thank you for the answer, and I thank you for seeing the video, and I appreciate all the participants, and we hope in the future everybody can come to São Carlos and do a stage in any of the many experiments we have in atomic physics. So now we're going to start a tour with real people, three-dimensional tour, and I hope that you guys that could not be present, the next time you'll be present, and we can enjoy you, and you can enjoy us even more than on the internet. Thank you very much, and